Hello, my name is Robert Abaticola. I am an IEEE senior member with a long career history in software engineering, technical operations, and technology in general. You're watching my Fast Abstract presentation for CompSec 2015 titled IoT Applications, Healthcare and Security Case Study. The Internet of Things has been around for many years, though the name's only about 15 years old. It goes beyond the interconnection of computers, networks, and related peripherals to include a multitude of other devices. For example, sensors for environmental equipment and health monitoring, home automation, manufacturing, agriculture, urban planning, and more. IoT is such a large area that there's no doubt there are many applications that we don't even know will exist in the future. This is why I state that for all of the major advancements in the field, the benefits are still largely unrealized. Healthcare is one of the areas where there's a great deal of research and development taking place, and for good reason. There's little more important to humanity as the health and well-being of its members. Because of the time constraints of the Fast Abstract format, rather than give a full introduction to IoT technology, I'm going to give an ultra-brief mention of a few points, starting with this concept of resource-constrained devices. This body area network illustration is a good example of an environment in which devices must be very small, lightweight, and unobtrusive. This necessarily means that they have to favor low energy consumption and low heat generation, which typically will come at the expense of performance, capacity, and bandwidth, to name a few. According to Tan and Koo, IoT technology can be divided into two categories: data acquisition and networking. Data acquisition can be achieved through the use of QR codes, barcodes, and RFID tags for identification, and sensors for taking physical measurements in the device's environment. The networking category of IoT technology is a much larger topic than can be addressed in our available time. So I give one example of a well-known and often used IoT communication protocol known as CoAP, which is the Constrained Application Protocol. As the name implies, it was developed specifically for use with constrained devices and networks. I'm going to talk about the case study itself now. It's called BuzzMe, which is a proof of concept implementation of a system intended for use in an assisted living or similar environment. The idea was to design a system that would enable an impaired individual and his or her caregivers to receive notifications of events that occur in the individual's home. The events could be as simple as someone ringing the doorbell, or something more urgent like an oven being left on for a prolonged period when nobody's home. These notifications have to be delivered in a way that overcomes the user's impairment. To that end, 3 sensory outputs are provided through an iOS application interface. Vibration motor patterns provide touch, visual cues provide sight, and audio cues provide hearing. Each type of output is unique for any given event type. The prototype system was built on an ARM-based hardware platform using ARM's Mbed web-based development environment and cloud-based device access and storage. A companion iOS app was written with Apple's then relatively new Swift language. The hardware should be very familiar to anyone who has used Arduino or similar prototyping systems. Illustrated here are the components that were used for this project. All of them are based on the Grove connection standard. As you can see in this block diagram, a separate vibration motor was attached to the system to mirror the feedback that was simultaneously provided by the iOS app. The app itself comprised a very simple interface on top of a polling engine that read event flags and sensor readings from the cloud device server and translated those into the outputs that were listed previously. Here are a few more technical details about the system. The controller allowed limited multi-threading, which enabled a few concurrent threads to run different functions. For example, the status LEDs on the main controller board were used to indicate heartbeat function, detection of motion, and error conditions. A temporary thread was used to initialize the Ethernet interface and to retry failed initialization. And a final thread was used for resource monitoring, and that was the actual reading of all of the physically connected sensors. Similarly, multi-threading was necessary in the iOS app. What was interesting about the app is at the time the code was written, there was no way to access an iPhone's vibration motor directly from Swift. Objective-C was needed to get that functionality. I'm going to move on from the project case study now and talk for a last moment on a couple of final slides about general security considerations. Anytime you put healthcare information and communication together, you have a serious need and even a legal obligation to protect the security of that data. For example, in the United States, HIPAA regulation specifies very strict requirements for ensuring the privacy of certain kinds of healthcare information. Military use of healthcare monitoring systems in the field is an interesting area in which the lives of soldiers could actually be dependent on the security of such systems. To me, it's not hard to imagine the outcomes of battles being influenced by the failure or integrity of this kind of monitoring. Studies of existing health monitoring systems have found that of various systems analyzed, most of them address basic needs like authentication and data confidentiality, but not one of them addressed all concerns. For example, the 2013 study cited here found that very little research into securing body area network communication had taken place. Clearly, there's a lot of work that can be done in this area. I want to close with an implementation consideration, or even a recommendation. Something that's not prominent in the published works is that widespread adoption of devices that make use of security features could easily be dependent on those features being as transparent as possible. Communication security schemes tend to be very technical in nature and invariably will add layers of complexity to a system. The suggested goal for any implementation is to design security from the user's perspective, and specifically that means making it as invisible and automatic as it can be. This is especially important in products aimed at the consumer market where ease of use may be critical to widespread adoption. Of course, this image here is intentional hyperbole, but it's meant to illustrate that the average consumer will resist any technology that requires a lot of learning, even if it's a lot less complicated than flying the Space Shuttle Endeavour. This concludes the presentation of my Fast Abstract paper for CompSAC 2015. Thank you very much for watching.